Okay, so I heard at least two of you might appreciate some chain rule review. So just like I did with the derivative, except probably shorter, I'm gonna go do the conceptual side first, then we'll branch over to the calculus and we'll do a bunch of practice problems. So imagine that you and me and a dog, we're all running a race. And this dog has some speed, which I'm calling V sub dog. And that dog is 3 times faster than you. So V sub dog equals 3 times V sub u. And then you are running twice as fast as me. So V sub u equals twice V sub me. So how many times faster is the dog running than me? Well, that would be the ratio of V sub dog to V sub me, right? Which I know is the same thing as V sub dog divided by V sub u times V sub u over V sub me, right? The V sub u's just cancel. And I know that V sub dog over V sub u, the dog is 3 times faster than you, so that's 3. V sub u over V sub me, the dog, you are twice as fast as me, so that's 2. So then just multiply those and you get 6. So the dog is 6 times faster than I am. That's scenario 1. Scenario 2, if you remember like doing dimensional analysis from chem last year, you could do all these sort of like unit conversions like this, where if I want to figure out how many minutes are in a day, I can use that there are 24 hours in a day, there are 60 minutes in an hour, and I can just multiply those because then the hours cancel and I'm left with units of minutes per day to figure out there are 1,440 minutes in a day. And this is the driving idea behind the chain rule, which is that, you have 2 rates of change. You have one thing that's changing because of another thing, but sort of like indirectly, and you have these like intermediary rates of change that you can sort of chain together, right, to figure out the one you're looking for. So here's how that looks in calculus. Let's say I want to take the derivative of tangent of 1 over x with respect to x. Well, I know that the derivative of tangent of x with respect to x is secant squared of x, and I can change that x to whatever symbol I wanted to, and that wouldn't change what the derivative is, right? It doesn't matter what letter I use. So that means that the derivative of tangent of anything with respect to whatever is, inside the tangent with respect to the argument is secant squared of that argument. So derivative of tangent of 1 over x with respect to 1 over x is secant squared of 1 over x. And then I know from my power rule, right, the derivative of 1 over x with respect to x is, you can just rewrite that as x to the 91st. Negative 1 comes out in front, subtract 1 from the exponent, and that's negative 1 over x squared. So I can then use these rates of change to figure out the rate of change that I'm looking for, which is this. So if you remember, the idea behind a derivative is it's a ratio of change in one thing over change in another thing. The only difference from average rate of change is it's in the limit as those changes go to 0. So it's an instantaneous rate of change. So this is a common Leibniz notation, W, is that it basically just represents that by using a D instead of a delta, right? I talked about this in the derivative video as well. So that's very nice because that means that here you can see that basically, these changes in 1 over x cancel out and you're just left with the ratio of change in tangent of 1 over x divided by change in x. This is technically an abusive notation. Keep in mind that it's not like these d1 over x's are literally canceling. It's the idea behind the derivative. Ratio of this to this, ratio of that same thing to a third thing, right? And so it's still, the idea still applies and it's almost as if they cancel. Anyway, derivative of tangent of 1 over x with respect to 1 over x, that's secant squared of 1 over x, derivative of 1 over x with respect to x, negative 1 over x squared, so you just multiply those two. And so the derivative of tangent 1 over x with respect to x is secant squared 1 over x times negative 1 over x squared. That's the idea. Let's do some practice problems. Generally speaking, the idea here is just, you have something and then you have, a function and then another function inside that function. So you just differentiate the outside with respect to the inside, and then you differentiate the inside with respect to x. Or if that inside has its own inside, then you differentiate with respect to that inside, and so on until you've differentiated with respect to x, and you just multiply all of those derivatives. Let's just do number 1. I'm using your chain rule problems sheet. So let's just say number 1. So derivative of sine squared of x with respect to x. This, if you're not super comfortable with it, the square can mess with you. So I'm going to rewrite this. Just note that this is the same as sine of x squared, right? So really we have a square with a sign inside of it. So that's what I'll differentiate first. The derivative of sine of x squared with respect to the inside, which is sine of x. And then I'll differentiate sine of x with respect to x. And so once I multiply those, then these ratios will give me the ratio of, change in sine squared of x with respect to change in x. So derivative of sine of x squared with respect to sine of x, that's the derivative of, pick whatever letter you want, u if you want to, derivative of u squared with respect to u. So that's just, actually let me write that. D u squared with respect to u. Derivative of anything, you can change sine of x to u in your head. Derivative of anything squared with respect to that thing is 2 times that thing, right? So here, our thing that's being squared is sine of x. So 2 times sine of x, that's this. Then derivative of sine of x with respect to x, we know that. That's just, I hate to say that's one of our formulas because I hate just memorizing formulas. But if you haven't proven this, then yeah, it's just a formula. So your derivative of sine squared is just 2 sine cosine. Let's do number 3. So derivative of, well, let's do number 2. Let's just start off slow. So derivative of sine of x. So our outside function here is sine, and our inside function here is also sine, which can be confusing. But basically, it's just the derivative of sine with respect to the thing that's on the inside of the sine times derivative of what was on the inside, which happens to also be sine, with respect to whatever's on the inside of that, which is just x. And that's what we're going for. So derivative of sine with respect to the inside is cosine of the inside. So that's just cosine of, and what was inside is sine of x. Then multiply by derivative of the inside, sine of x with respect to x, which is just cosine of x. Okay? And then of course, if you want to do number 3, which is just the same thing, but there's another sign in there, then again, it's just derivative of sine with respect to, maybe I should even underline this, stuff on the inside. That's the idea. Derivative of sine with respect to stuff on the inside. So that's just cosine of stuff on the inside. What's on the inside here happens to be sine of x. Then derivative of the inside, which is sine of x, with respect to whatever is on the inside of it, which is again sine of x. Not again, but yeah, right? So the idea is just inside. Derivative of sine with respect to the inside is cosine of the inside. So that's cosine of sine of x. And then lastly, derivative of the inside with respect to whatever is inside of that, which is just derivative of sine of x with respect to x. So cosine of x. Okay, and I think you can see how it would work for number 4, which is just sine of sine of sine of sine of x. Then let's jump down to number 5. So let's do the square root of x squared plus 5x. Obviously your outer function is the square root, your inner function is this x squared plus 5x. So let's differentiate the square root of that with respect to that. So the square root of x squared plus 5x with respect to x squared plus 5x. And again, this is a ratio, right? And change of that square root with respect to stuff inside the square root. And then we multiply by change in stuff inside the square root to change in x. So then you're left with just the ratio of the change in this square root with respect to x. Derivative of the square root of something with respect to whatever is inside of that square root. That's the same. So the square root of x is the same thing as x to the 1/2. So square root of u, x to the 1/2. 1/2 comes out in front, and then subtract 1 from the exponent, so negative 1/2. So here, that's 1/2 times whatever is on the inside, because we're differentiating with respect to the inside. So 1/2 times the inside, which is x squared plus 5x, to the negative 1/2. And then here, derivative of x squared plus 5x. Power rule this, right? So 2x. You can power rule this, or you can just think about this is a linear function, and it has a slope of 5. So its derivative will just be 5. And so the derivative of this guy is that derivative times that derivative, which is this times this. So there's your final answer. Let's do number 7, using the next negative x squared over 5. All right, so our outer function is e to the something, right? So you could think of it as e to the x, although that gets a little confusing because there's already an x here, but anyway. So derivative of e to the negative x squared over 5, change in e to the negative x squared over 5, divided by change in negative x squared over 5, then multiplied by change in negative x squared over 5 over change in x. Derivative of e to the something with respect to that thing is just the same thing. So this part is just e to the negative x squared over 5, multiplied by now the derivative of negative x squared over 5 with respect to x. This negative and the 1 at the over 5 are just like a coefficient, right? So they stay. And then the 2 comes out in front. So you get negative 2/5 x to the first. Ooh, this one's kind of fun. Derivative of 1 over cosine of x. This one lets us prove one of the things that you had to memorize before. Chain rule, my goat. So first of all, that's 1 over something. So there's our outer function. The derivative of 1 over cosine of x with respect to sort of its argument, which is cosine of x. Then multiply that by derivative of that guy, change in that guy, divided by change in x. Derivative of 1 over something with respect to that thing. Let's say it's 1 over u with respect to u. 1 over u is u to the negative first. Negative 1 comes out in front. That's negative u to the negative 2, which is negative 1 over u squared. So derivative of 1 over cosine with respect to cosine is negative 1 over cosine squared, multiplied by the derivative of cosine, which is negative sine. And then if you do a little simplifying, these negatives cancel. You get sine of x over cosine of x times 1 over cosine of x, which is tangent of x times, and then 1 over cosine of x is secant of x, which should look awfully familiar because that's the derivative of secant of x. And look over here, 1 over cosine is just secant. Let's jump down to 11. All right, derivative of, what is it? 3 to the cosine x with respect to x. So our outer function is 3 to the something. So change in 3 to the cosine x divided by change in cosine, multiplied by change in cosine, divided by change in x. So derivative of, some number a to the power of u with respect to u, that's natural log of a times a to the u. So here our a is 3 and our u is this cosine. So that's natural log of 3 times 3 to the cosine of x. That's this part. Derivative of cosine is negative sine of x. Natural log of cosine of x cubed plus 1. Let's do that one. Our outermost function is going to be natural log. So let's do the derivative of natural log of cosine of... By the way, you don't have to write all of these like derivatives like multiplying each other every time. I generally don't, but for the sake of like showing you why the chain rule works and like why we do this. And also it's nice because it helps you check that you like are multiplying the right derivative by the right thing, because you can check like, is this the same as this and all of that. So like don't feel like you have to, like your Gamble's not require that you write this on a test or anything. And once you get like comfortable with it, you're not gonna need to. So derivative of natural log of that stuff with respect to that stuff. That stuff being cosine of x cubed plus 1. Then derivative of cosine of x cubed plus 1 with respect to whatever is inside of it, which is x cubed plus 1, multiplied by derivative of x cubed plus 1 with respect to whatever is inside of it, which is just x. Derivative of natural log of whatever with respect to that is 1 over that thing. So 1 over cosine of x cubed plus 1. Hang on, the 1 over is coming. There you go. So 1 over cosine of x cubed plus 1, that's this part. This part, derivative of cosine with respect to whatever, is negative sine of that. So times negative sine of x cubed plus 1. Derivative of x cubed plus 1 with respect to x. 1's just a constant, so it's going to go away. 3 comes out in front, drop it down, so you get 3x squared. So times 3x squared. Let's do natural log of cosine of x cubed plus 1. How about that? That part is cubed, and then you add 1. First of all, our outermost thing is really 2 things being added. The 1 is just a constant, so don't worry about it. This is basically a cube with some other stuff inside. So derivative of that stuff cubed, and that stuff is natural log of cosine of x with respect to that stuff, natural log of cosine x, times derivative of natural log cosine of x with respect to cosine of x times derivative of cosine of x with respect to x. Derivative of a thing cubed with respect to that thing is the 3 comes out in front, drop the exponent, so it's that thing squared. So this is a natural log. Oh, wait, 3 comes out in front. Sorry, it should be 3 that thing squared. So 3 natural log of cosine of x squared. Then this is, let's see, derivative of natural log with respect to the inside is 1 over the inside. Derivative of cosine is negative sine. So there you go. And then just to show you what this would probably look like if you're not writing all of the derivatives, let's do cosine of 1 over x. So derivative of cosine of 1 over x is a derivative of cosine with respect to the inside, so that's negative sine of the inside, multiplied by the derivative of the inside with respect to x, so that's negative 1 over x squared. Let's do one more. Let's do sine of e to the x squared, and we'll call it. So our outermost function here is sine. So we'll do change in sine of the inside with respect to the inside, multiplied by change in the inside, divided by change in whatever's inside of that, which is x squared multiplied by derivative of x squared divided by change in x. Derivative of sine with respect to the inside, cosine of the inside. Derivative of e to the something with respect to that thing is just e to that thing. Derivative of x squared is the 2 comes up in front, drop the exponent down by 1, so it's x to the first. Cosine e to the x squared times e to the x squared times 2x. Chain rule is really the main thing that you were missing when it came to deriving all of those derivative formulas from last unit. So really, if you wanted to, and I encourage it, but obviously like not everyone's up for all that. If you wanted to, you could go back and I think it wouldn't be too hard. But yeah, I'll leave it at this. Just remember the idea of chain rule is basically you have a bunch of all of these sorts of you have a bunch of related, change in one thing with respect to another thing, change in that second thing with respect to a third thing, and so on. So you basically just multiply those ratios to get the ratio that you're looking for. That's the idea behind chain rule. We have a website. I'll probably link it in the description. We have math labs every Tuesday and Thursday. If you need tutoring, it's kind of our thing. So don't hesitate. But yeah, I've been Garrison. Math over, plug over, video over.